recording is on. So someone is asking about the 290. So let me see what 219 is. Problem. Which specific problem do you have? Does anybody know which specific problem you have? Hello? Somebody wrote on messages again. Okay, 2.19 G. Okay, for example, okay, so 2.19 G is xn plus 1 equal 2 to the n xn plus n for x1 equal to 1. Okay? Well, you need to use the formula. The formula says, recall, if you have, let me see what the equation is. So if you have xn plus 1 equal to an xn plus gn xn, so the solution is xn is, I'm reading from the book, in 2.2, is x naught, the product, s equal xn naught to n minus 1 as plus r equal n0 to n minus 1, the product of s equal r plus 1 to n minus 1 as g of r xr. Okay? So this is what we have. So for our case, xn is x naught is 1 times the product s equal n minus 1 2 to power s. Correct? Plus r equal 1 to n minus 1, s equal r plus 1 to n minus 1, 2 to power s, times r3. Okay? So it's most likely sometimes you may have to leave it like that. I mean, in some cases I could accept this, but you should be able to do so for example, in some cases, if you guys cannot evaluate this, leave it like that, okay? If you are having problem with the evaluation. But some are easy to evaluate. And it happened, I don't give you the answer to this one. And so, answers. So you may leave it like that because I really don't want to take the time. But I could easily this is S equal R plus 1. So this is going to be difficult to do. What you're going to have to do is summation by part here. Summation by part. This one here. And so you may remember it's the sum of this. You may take this one del X and this is EY or something and do integration by parts. Okay? Summation by parts. So why don't you go ahead and try it? See what you can do with it. If not, just leave it like that if you cannot do much with it. Okay? So this is okay. So the only worry is about this one, but you must do summation by parts. All right? Do you have any other questions? So I'm asking you if you can do the integration by parts, do it. If not, just leave it like that. Okay? Any other questions? And I really don't want to take much time, and just to save time, I will work it out for you today, and I will share it with you tomorrow, or I will upload it on Canvas. Okay? I forgot to send an announcement regarding the midterm. So it's gonna be on Sunday. I'm gonna get it started at 10 o'clock. And I said, I'll give you what, 6 hours, 8 hours? How much? I will decide.
You said it's gonna be 8 hours.
8? All right. So that will be around 6 o'clock. Okay. All right. So I will post it at 10 till 6. All right. Any questions? Too new. Okay. I can hear people saying 8 hours, 8 hours. Okay, we'll do that. All right. Any other questions? So again, I'll try summation by parts on this problem, and I will try it for you too myself. Okay. All right. So we're gonna go back to the Z transform. The Z transform is for a sequence Xn is this equation here, this formula. All right. And we did last time. Last time we defined UN, and this is a unit step function, is 0 for n less than 0, 1. And then we looked at it is Z transform. So there is only, it's 1 for n bigger or equal to 0. So you replace with 1, and Z to the minus n is Z over Z minus 1. Okay. And the delta function, remember, delta n is 1 for n equals 0 and 0 for n different from 0. So the Z transform of it turned out to be, well, there's only some meaningful out of it is when n equals 0. When n equals 0, you get del 0. Z minus 0 is 1. So you get del 0, Z minus 0. You get del 0, but del 0 is 1. And that's it. Okay? All right. Now, we're going to do scaling. We are going to do scaling. So we're gonna go like, it's like similar to the Laplace transform. All right. So this is section 3.3 scaling and shifting. Okay, so you really don't want to use the definition to find the Laplace Z transform of any different function. Once you do the base one, the foundational one, and then you can manipulate using some theorems or some result to do other function. All right, so let's say theorem 3.3.1, that is about scaling. So we're gonna let Z of UN, this is the regular U, not this is not the unit step function, just regular sequence U, equal to UZ, then D of A minus N UN is equal to UAZ. So whatever you do here, it's UAZ. This is one.
Hey, Professor,
Yes.
could you rotate the right side of the board? There's a big glare.
Is that better?
Yeah, that's perfect.
Okay, thank you. All right. Yeah, it's actually I have the drape. That should help a little bit. Believe it or not, I have 13 windows on the front side of the house. So it's like they bring a lot of sun and they're big windows. All right. And Z A to power N UN is U A over Z, or Z over A, sorry. Okay, let's do the proof of one. What is Z of A minus N UN? That is N equals 0 to infinity, A minus N UN Z minus N. Okay? And so this is N equals 0 to infinity UN times AZ minus N. Recall, what is this? This is N equals 0 to infinity UN Z minus N. This one, by definition. Look, the Z is being replaced by AZ. So this is U of AZ. What is U of AZ? U of Z is that, U of AZ, you replace Z by AZ, and that's it. Okay? The proof of 2, AN UN, is N equals 0 to infinity, AN UN, sorry, AN UN Z minus N, and that is N equals 0 to infinity UN times Z over N to power minus N, and that is U of Z over A. Okay? So that is the scaling. For example, let's say I want Z of 2 to the N sine N theta. Well, we're gonna let uz equal to the z of sine n theta, okay? Because that is this one is this one. You see? And that is the un. So the uz is z to the n theta. Do you remember we did this last time? What is that? Is z sine theta over z squared u squared z squared minus 2z cosine theta plus 1. That is uz. So hence z of 2n sine n theta is u 2 z over 2, and that is uz here. So that is z over 2 sine theta over z over 2 squared minus 2z over 2 cosine theta plus 1. Okay? So that's how you do it. Any questions? I'm just giving you a couple minutes to look at it. All right. So let us move on to something else. So now with the Z transform, there are differentiation too. So theorem 3.32, derivatives. Okay. For a positive integer p, we have z to the n p is equal minus z d of dz. This is the first derivative with respect to z. of Z and P minus 1. Okay? All right. Now, here is a proof. Okay? What is Z and P is n equals 0 to infinity np z minus n. Hence, z and p minus 1 is n equals 0 to infinity np minus 1 z minus n. Okay? All right. So we're going to differentiate then d of dz of z of np minus 1 is n equals 0 to infinity np minus 1. Now remember, I am differentiating with respect to z. So that will be minus n z minus n minus 1. I am going to pull out minus z minus 1, and I'm going to have z equals 0, and p minus 1, and z minus n. And that is minus z minus 1 n equals 0 to infinity and p z minus n. And that is minus z of np, isn't it? Oh, I have z minus 1, sorry. Okay, so solve for z and p and get z and p here on both sides. So we said we have 1 minus 1, sorry, if I multiply by z, so we get minus z d of dz z and p minus 1 equal z and p. Okay? I have this one equal to that one. Just solve for z and p. So go ahead, find z of n. Go ahead. This is an example. Try to find it on your own. Go ahead and do it. Let's see. Practice. See what you can do. Well, so for z to the n, so here p is 1. So we are doing zn is minus z times d of dz of z of n to power 0, that is minus z d of dz of z of 1. And what is z of 1, guys? That is minus z d of dz times z over z minus 1. You take the derivative of that. Okay? So this is equal minus z. It's the derivative of the top is 1 times z minus 1 minus z over z minus 1 squared. Okay? I use the quotient rule. The derivative of the top times the bottom minus the top times the derivative of the bottom, which is 1, over z minus 1 squared over bottom squared. Z minus z, so this is z over z minus 1 squared. And of course, that is z bigger than 1. Okay? So now we found z to the n. So what about zn squared? Well, that is minus z d of dz of z to power n. Isn't that correct? I'll put the p equal 2 here. If p equal 2, you get z of 1, z of n to power 1. So what is z of n? So that is minus z times d of dz of z over z minus 1 squared. And you can figure it out. You can take the derivative again. Okay? Any questions? So these are all right. Okay. Now, what if we multiply by n? Okay, this is theorem 3.3.3. Multiplication by n. So that un be a sequence with z of un equal uz. Then z of nun is equal to minus z d of dz uz. Okay? Any questions so far? I'm gonna do a few proofs here because this will show you some manipulation, how to manipulate discrete systems. That's why I'm really trying to do some examples and some proofs. So let's do the proof. So we have z of nun, just apply the definition. Is n equals 0 to infinity, n un z minus n. Okay? Now, I can write this as n equals 0 to infinity minus n un z minus n minus 1, and I multiply by minus z. Isn't that the same, guys? The minus will give you plus n, un, z times z minus n minus 1 is z minus n. So all I did is I just rewrote it. Okay? And that is minus z n equals 0 to infinity of d of dz of un z minus n. Remember, the derivative is with respect to z. And that is minus z d of dz n equals 0 to infinity un z minus n. But this one here is nothing but uz. Look at it. So this is uz. So this is minus z d of dz uz. Okay? So for example, if you want the z transform of n sine n theta, that is minus z d of dz u of z, or z of sine n theta, and that is minus z d of dz. What is the Laplace transform of the sine? So that is z sine theta that minus d sine theta over z squared minus 2z cosine theta plus 1. There. Okay? Any questions? All right. Any questions so far? Okay. Let us do for a little bit more. Theorem 3.3.4. This is shifting. Could be to the right or to the left. So that's let z of un equal uz. Then for a positive integer k, we have 1 v of un minus k is z minus k uz plus m equal minus k to minus 1 um z minus m, and this is for n bigger or equal to k. So this is right shifting. So you are shifting the sequence to the right. Okay? Two, z of un plus k is z to the power k uz minus u0. Now this is a small sequence. Minus u1 over z minus u2 over z square minus, and then uk minus 1 over zk minus 1. So that is left shifting. Okay? I'm gonna do the proof of the first of the second one. It's a little bit difficult than the other one. All right, so we're gonna do the proof of 2. Okay, let's take a few minutes break and then come back to it. Maximum 5 minutes break. Okay, we'll be right back. All right. Let's come back here. So un plus k is, let's use the definition, n equals 0 to infinity un plus k z minus n. Okay. So we're gonna let j equal to n plus k. Then this is equal to n equals 0, j equal k to infinity uj z of minus n k minus j. Okay. So far, so good. So let's take the summation is done over j, so we can take zk out. You see it? And then j equal to k to infinity uj z minus j. So I am going to go z to the k. So I have, look, I have, this is k minus infinity, infinity. Okay. And I really don't know, I mean, n plus k, and let's say 0 is here. Okay. So I am going to, you have uz. uz mean I need from 0 to infinity. So this is a j equals 0 to infinity uj z of minus a j. So I went from 0 to infinity and then minus, but 0 to infinity minus infinity to k, and that will give me j equals 0 to infinity, j equal k. Okay, so I'm gonna subtract minus summation m equals 0, okay, to k minus 1. All right. umz minus n. There. So I went from j equals 0 to infinity minus m equals 0 to k minus 1, and then that will pick up j equal k to infinity. Now, this is z to the k. This one is uz, and then minus m equals 0 to k minus 1 um z minus n. Okay? And then if you put 0 in for m equals 0, you get minus u0 for m equals 0. Okay? m equals 0 mean k equals 0, zk. M equal 1, okay, that means k equal to 2, and then you will get the second term and so forth, okay? And that's what we have here. Minus u1 minus u2 and so forth. So that is a proof of 2. All right, any questions? Now, so we do have a corollary immediately. This is corollary. For those of you doesn't know the meaning, corollary mean it's something that follows immediately from something else. So we call it corollary. And mostly they don't need to be proved. So let xn be a sequence for n bigger or equal to 0. Then for zxn equal x of z, we have 1 z of xn plus 1, z of xn plus 1, that means k is 1, that will be z xz. And if k is 1, then that you gotta stop. K is 1, this is u0 over 1. So minus x of 0. You see that? You see how interesting it is, how easy it is? So it follows, just set k equal 1 here. So the last term immediately disappears. So you have z, uz, okay, xz minus k equals 0. K, this will be m equals 0, u0. All right. For 2 z of xn plus 2, that is z squared x of z minus x of 0 minus x1 over z. Okay? And what should this remind you of, guys? 3 z of xn plus 3 is z cubed xz minus x0 minus x1 over z and minus x2 over z squared. There. Well, this should remind you for Laplace transform that the Laplace transform f prime of t, remember? And L f second of t and L f third of t. But here we did it for kth derivative. So I did it for the kth derivative.
Hey, Professor,
Yeah,
for the bullet point 1, you just have z multiplied by x of z, but then for 2 and 3, it's z squared is multiplied by the entire sequence. So
no.
there a parenthesis there? Okay.
Yeah, this is correct. Because,
All right.
okay, just give me a second here. Let's, your, yes. Okay. minus zx or minus zx0. All right. Let's see. Minus x0 minus u1. Yeah. Okay. All right. Any questions? Let's see what am I gonna do next. This is 93. I'm just looking at my notes. So I do some shifting. So let's say by 1 unit. Let's say I have AN, and that is the graph of it. It's 1, 1/2, 0, at 2, this is 1, 2, 3, 4. Oh, actually, I take it to be even. Okay, 1, 2, and then okay, let me take it like this here, and let me take it at 4 to be this one here, even smaller. So how is this shifted? AN minus 1. So the 0 becomes 1. So that is this one, 1. So this is the 0. The 0 becomes 1. And the 1 becomes 2. The 2 becomes a 3. Okay. The 3 becomes 4. The 4 becomes 5. You see how the sequence is shifted? This is AN minus 1, and this is AN. So you just shifted by the right. It's like a graph, but you shift the point. Okay? All right. So basically, all you have to do is you are like, it's like a delayed sequence. And the delay is 1. So that is like a delayed sequence, and the delay is 1. All right. Okay, so definition, 3 3.3.1 for positive integer k, the unit step sequence uk of n, or un of k, sorry. This is different than the other u, is 0 for 0 less or equal to n less or equal to k minus 1, and for 1 for n bigger or equal to k. For example, u n of 5 equals 0 for 0 less or equal to n less or equal to 4, and 1 for n bigger or equal to 5. Okay? So if we look at the sequence, that will be 0 here, will be 0 here, will be 0 here, n equals 0, n equal 1, n equal 2, n equal 3, n equal 4, and then at 5, it jumps to 1 and stay at 1. You see that? So that is u n of 5. Okay? And that is 0, 1, 2, 3, 4, 5, 6, 7, 8, and so forth. Okay? So now let's see what kind, because this in signal analysis, this is very important in engineering. And let's see what is the Z transform of such a sequence. Okay? And now we're gonna do all right, theorem 3.3.5. Let AN be a sequence with Z of AN equal AZ. Then for a positive integer k, we have that the Z transform of the AN delayed by k un of k is equal to Z minus k AZ. Okay? Why don't you just fiddle with the proof of this on your own for a minute, see what you can do. Try to apply the definition of the Z transform and see what you can do with it. Just for the 2 minutes, I need you to have a feeling of why the proof works that way. All right. So let's start from the definition. Uh, Z minus N. That is basically the definition. So if we let J equal N minus K, this becomes N equals 0, J equal minus K, okay, to infinity, A, J, UN of K, I'm gonna leave it alone. And Z of minus N is minus J minus K. Well, J equal minus K to infinity, so you will see how this is defined. This is 1 because of the definition. And for N bigger or equal to K. So that is J equal minus K. What do you think is going to happen? So we have N equals 0, U N K. So I am looking at J U N. UN is a J plus K here. And this is going to be, we're going to use the property J equals 0 to infinity, AJ Z minus J minus K. Okay? Because the other one did J and so for a J equal minus K, for a J all the way up to J equals 0. For a J equal minus K, J equal minus K, U0 is 0. Okay? So for N bigger or equal to N and UN for K, for this definition here. So we need everything up to 0 is 0 for this. So and then from 0 and above, this is 1. So we're gonna replace it by 1 J minus K. Okay, so I am summing over J, so I can take the Z minus K out. J equals 0 to infinity, AJ, which is, I think my wife wondering why I keep calling my granddaughter out. Her name is Aurora Jane, so we call her AJ. So AJ and Z minus a J. And you can see that Z minus K AZ as I claimed. Okay?
Actually, when you said to infinity, I wanted to yell and beyond.
And beyond. There we go. All right. So let us do an example. And this is example 3.4. Let's say we want to find z of u and k. Well, so here a is 1, and so az is z over z minus 1. And so this one equal to z minus k times az, and that is z minus k times z over z minus 1, and that is z1 minus k over z minus 1, and for z bigger than 1. Okay? You see what happened? And then you can do so many other things with it. Let me do one more example, then and I will stop here. All right, here's another example. Just go ahead and finish this one. All right. All right, so this is another example. Example 3.5. Find z of an, where an is 3 for 0 less or equal to n less or equal to 10, and 4 for n bigger or equal to 11. So we notice that an is 3 plus un at 11. Let's see why. Okay. Well, for n bigger or equal to 11, the an is 4. So for n bigger or equal to 11, this is 1. 1 plus 3 will give me 4. For n less or equal to, so basically here your k is 11. And if you look at the definition of un, the unit step for n less or equal to k minus 1, which is 10, is no, for the u, this is 0, and then you will get with an equals 3. Is that clear? Hence, z of an is z of 3 plus un at 11, and that is 3 z of 1 plus z of un at 11. Remember what is un of k? Look at that. Un of k is z to power 1 minus k over z minus 1. So remember, k is 11. So what is z of 1? Plus this one is ZUNK is Z1 minus K. So that is Z1 minus 11 over Z minus 1. There we go. Okay? So that's how you find it. Okay, I'm gonna stop here for today. All right. And I hope you're watching the videos, because in some places, if you may think I'm going a little bit fast, so you can go back to the video, slow it down, or pause it, or see other stuff, see whatever you need to do. So this is like very much Laplace transform. And you know, I did my dissertation in this discrete system. So I was able to take a lot of the continuous case, and most of this theory is developed by me in my dissertation. And then later on in life, I continued with it, and I proved so many other things later on. And so this is really my subject. Anyway, I'm gonna stop here. Do you have any questions?
Yeah, Professor, do you know, is the exam going to cover up to homework 4 or homework 3?
Okay, let me think about it. Okay.
All right.
All right.
Sounds
Any other questions? It's funny that let's see who's here. Yeah. All right. I'm gonna stop. I'm gonna stay online, meet with the student. So I'm gonna only stop recording.